welcome to our third exam review. In this particular test, we're going to start off by modeling various teaching techniques. So what I'm specifically looking for in these types of questions is not that you know the answer, it's that you know how to demonstrate a particular model and how to justify that answer. Okay, so like in number one, I understand that we know what 8 minus a negative 4 is. You know, 2 minuses make it a positive, so 8 plus 4 is 12. I get that. In order to earn credit for this, though, you need to demonstrate that you can answer that question using what's called the charged particle model. Okay, so the charged particle model is, we need to start off with 8. That's our first number. So I'm going to draw 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I start off with 8. And then subtracting means that I'm going to take something away, and I want to take away a negative 4. Well, right now I don't have negative 4 to take away, but I can always add 0. And so in adding 0, I'm going to add, what's called a 0 pair. So I'm going to plus and a minus at the same time, which cancel each other out. But I'm going to add 4 of those. Okay, so now I have the ability to take away negative 4. So in my drawing, I would indicate that I'm going to group the negative 4 and take it away. And then I'm left with the 12 positive charges. So 8 minus a negative 4 is 12 using that illustration. So what I'm looking for is that actual picture on something like this. Number 2, 5 times negative 2. Well, 5 times negative 2, I need 5 sets of negative 2. So you kind of have to think, what would that look like? Well, if I have, there's a set of negative 2. There's another set of negative 2. There's another set of negative 2. So I've got 1, 2, 3, 4, 5 of those. So just group them together and show that there are in fact 5 sets of these things. And so together they end up giving us negative 10. The number line model, of course, starts with a number line, so I'm going to go ahead and sketch that. And when we're adding two numbers, then that first number tells me where to start at. So I'm just going to put 0, 1, 2, 3, 4, and 5. Okay, so I start at 5, and I'm going to add a negative 1 to that. So negative 1 means I'm just going to go back 1 unit, and that puts me at 4. So the answer to that particular question is 4. And again, I'm looking specifically for that picture. In the number line model for multiplication, so we're going to start with this, and I'm going to start with 0. So the 5 represents a speed, and the 2 represents a time. Okay, so the fact that it's negative 5 means I am facing that direction. So I'm facing towards the negative numbers. And we're going to say that that 5 represents some sort of speed, that I'm going 5 miles per hour. And the negative 2 then represents some sort of time frame. So what we're saying then is, if that's the direction I'm heading, where was I 2 hours ago, considering that I'm at 0 now? So 2 hours ago meant, or an hour ago I must have been at 5, and then 2 hours ago I must have been at 10. So negative 5 times negative 2 puts us at 10. In the area model, I need to start by modeling each fraction independently of each other. So 3/5 means I'm going to look at, let's see, make sure I get that counted correctly. Yeah, there's 5 there. Okay. So 3/5 means I'm looking at an object that's been chopped up into 5 equal pieces, and I'm looking at 3/5 of them, so 3 out of the 5. And then 1/2 means I'm looking at an object where I've only shaded half of that. So what I'm going to do then is I'm going to convert the 3/5 and the 1/2 into a common denominator, and in this case tenths. So the easiest way to do that is to redraw that 3/5 picture. One more. Okay, and I'm going to connect a line going down. So now I've got 10 equal pieces, but now I'm going to shade the same number of, same area, but now I've relabeled it so that it's 6 out of 10. And then the 1/2 I'm going to do sort of the same thing. So I'm going to convert the 1/2 into 5/10. All right, and so shade, again, 5 out of the 10. And now when I go to combine them together, I've got two rectangles that I can sort of fill in the blanks in. So I'm going to start by filling in one of them. And it turns out if I count, I have 6 here and 5 here. So I've got all 10 of these filled in. And then I actually have another one where I've got 1 left over. So that equals 1 1/10. Okay, so again, that's what I'm looking for, the pictures and being able to demonstrate that. On number 6, show the following are equivalent fractions using the LCM method. So I need to first calculate the LCM of the denominators. So I need the LCM of 36 and 24. And I'm kind of leaving this very open-ended as far as how one goes about finding that. One method we talked about was intersection of sets. Let's see, so I'd break up 24 into its prime numbers. So that's 2 times 12, and then 12 is 2 times 6, and that's 2 times 3. And 36 would be 2 times 18. 18 is 2 times 9, and then 3 times 3. And so when I look at the LCM then, I know it's got to have at least 2 cubed in it. And then I can see it's got to have 3 squared in it. So that's 8 times 9, or 72. And again, this is one method, so using the LCM, using intersection of sets. And last unit we talked about a couple different ways to do that. So I'm just, find the LCM. That's what you got to do. So then what I want to do is I want to convert 15 over 36 into a fraction in terms of 72. So I end up multiplying by 2 to get that. So I'm going to multiply by 2 there. That gives me 30. And then I want to do the same thing with 10 over 24. So in terms of 72, I multiply by 3 to get that. So if I multiply the 10 by 3, I get 30. And of course, the two fractions equal each other. So we're good. So at that point, that's enough to say that 15 over 36 is equivalent to 10 over 24. Okay. But again, what I'm looking for again, since I'm asking you to demonstrate the LCM method, I'm looking that you can find the LCM and that you can show me how you convert each fraction into another form using that least common multiple. In this next set, we're going to look at simplifying each expression. If it turns out there's nothing we can do to simplify it, then our final, it would just write NR, which simply means that there's nothing we can do. It's not reducible at all. So the short version here is we're looking at just some algebra rules, just making sure that we can simplify expressions algebraically, that we can handle fraction rules and that sort of thing. So here, we've got -2 subtract 7 plus 10. So order of ops says that I want to add 7 plus 10 first. And then with the two signs, -2 minus 17 is -19. So that's that. Number 8, we are multiplying. So I just want to make sure that we know how to either FOIL or double distribute, whatever you want to call that. So that's x squared minus xy plus xy minus y squared. And I should notice that the middle two terms cancel out, and I'm left with x squared minus y squared. So I'll give you something that will require you to FOIL it out and multiply. Then number 9, okay, that numerator should look real familiar. That's a variation of the difference of two squares, which is what we did in number 8. So the factored form simplifies to x plus b, a plus b and then a minus b divided by a plus b. And hopefully we notice that the a plus b's cancel out. And I'm left with a minus b. And then the last one is using our fraction rules. So our common denominator would be a plus b times a minus b. And that first fraction, so that 3 was missing the a minus b in the common denominator. And the second fraction was missing the a plus b, so that's what I'm going to multiply by. And then I just need to simplify from here. So that works out to be 3a minus 3b minus 5a minus 5b, still over a plus b and a minus b. Okay, so kind of keep simplifying here. Up top, what do we got? Negative 2a minus 8b, and that a plus b, a minus b, that's our difference of two squares. So I can multiply that together. And at that point, there's not too much I could do. I could, so that's actually a fine answer. There's one thing I can think of that we can do, and that's factor out a negative 2 up top. Maybe see if anything divides out, but it's not. Okay, so a plus, factor out a negative 2. And I think both of those answers are sufficient to give you full credit. Again, what I'm looking for is that you can use your fraction rules and that you can reasonably simplify it down to an expression that makes some sort of logical sense. Okay, I'm a big fan of difference of two squares. I think there's a lot within that pattern that we should be able to demonstrate. So number 11, I'm asking you to demonstrate that you can handle a quite unusual form of difference of two squares. So here we got x plus y squared. So we're going to say that's our first number minus the second number. And we're going to have 2 of those. That's what the difference of two squares pattern looks like. So in that first blank, we're going to do x plus y and x plus y. And in the second blank, we'll have a z. So this works out to be x plus y minus z and x plus y plus z. And that's it. That's all I asked you to do is to factor that. So that is a perfectly fine answer.